In this lesson, we're going to talk about how to calculate the electric field at a point due to a point charge, but we're going to do it two ways. We're going to do it the old-fashioned intuitive way, and we're going to use the electric field vector formula to get the same answer so that you could understand how it works. So, in order to calculate the electric field at point P, because it's a vector, we need to know the direction of the electric field. To find the direction, we're going to draw an arrow from the source charge to the point of interest. So the electric field is going to be emanating away from the point charge towards point P, and that's going to be the direction. Now we could turn this into a triangle. Let's define the charge to be the origin. And to get to point P, we need to travel 3 units to the right, 4 units to the left. To keep this simple, let's say this is in meters. So this is going to be 3 meters to the right, 4 meters up. And our goal is to calculate the electric field at point P. Now, this formula gives us the magnitude of the electric field at some distance r. Now, using Pythagorean theorem, we could find out what the distance r is. R is the distance from the charge to point P. So this is r. And we could see that this is a 3, 4, 5 triangle. So r is 5. Using the Pythagorean theorem, c, or in this case r, is going to be the square root of a squared plus b squared, or the square root of 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 is 5. But if you know the 3, 4, 5 rule, you'll know that r is 5. Now, k is a constant. K is 9 times 10 to the 9 newtons per square coulomb per square meters. Q is the charge in coulombs. Q is 100 microcoulombs, but we need to convert that to coulombs. So we just got to replace micro with 10 to the minus 6. And R is in meters, so R is 5 meters and it's squared. So we can see the unit meters squared cancels. Only one of the coulomb units cancel. So we get the electric field in newtons per coulomb, since we have 1 coulomb left over. So it's 9 times 10 to the 9 times 100 times 10 to the minus 6 divided by 5 squared. So we get the magnitude of the electric field as 36,000 newtons per coulomb. Now we can calculate the angle of the electric field vector using the inverse tangent formula. So this angle is going to be arctangent, and it's going to be the y component over the x component. So this would be Rx. Let's say this is the position vector. Rx is the horizontal component. Ry is going to be the vertical component. So Ry is 4, Rx is 3. So arctangent 4 over 3 gives us an angle of 53.13 degrees with respect to the positive x-axis. So now we could describe our answer like this. So the electric field is 36,000 newtons per coulomb directed at an angle of 53.13 degrees from the positive x-axis. So that's the old-fashioned way of solving this problem. Now we can also represent our answer using the unit vectors I and j. So the electric field vector is going to be the magnitude times cosine of the angle 53.13 times unit vector I plus the magnitude times sine of the angle times unit vector j. So 36,000 times cosine 53.13 gives us 21,600 times the unit vector I. And 36,000 times sine 53.13 gives us 28,800 times j. So this is another way in which we could represent the answer. So we can write the electric field vector in terms of its components with the unit vectors I and j, or we could describe it with magnitude and direction, with the magnitude and the angle. So both answers are correct. Now, if we were to use the electric field vector formula to get the answer, it will give us the answer in this form. But I want you to see how we can get the answer the old-fashioned way. But let's use the second method to solve this problem. So here is the electric field vector formula. It's kq over r squared times that thing, r hat. What is that? Now, if you're wondering what r hat is, we'll talk about that shortly. First, it's good to understand the basic components of a vector. There's two important parts of a vector. Every vector is composed of magnitude and direction. Keep in mind, a scalar quantity only has magnitude, but a vector quantity has both magnitude and direction. So the vector v, for instance, can be written as the magnitude of the vector times its direction, which will be v hat. The position vector is basically the magnitude times r hat. R hat is what is known as a unit vector. Now you might be wondering, what is a unit vector? A unit vector is a vector that has a length of 1. It's the vector divided by its magnitude. That's how you calculate the unit vector. The purpose of a unit vector is to give the original vector direction. Because let's say you have a magnitude of 5 and you multiply it by something that has a magnitude of 1, well, it doesn't change the overall magnitude of the vector. It remains 5. So that's why the magnitude of a unit vector must be 1. However, the unit vector can give direction to the original vector, and that's its purpose. So a unit vector is a vector whose length is 1, but it has direction. So when we apply this to the electric field vector formula, we have the electric field E. This part of the equation tells us the magnitude of the electric field. And the magnitude is kq over r squared. R hat is the unit vector. It tells us the direction of the electric field. So make sure you understand the way this equation is designed. This is the magnitude of the electric field. This gives us the direction of the electric field vector. And to get r hat is the position vector divided by the magnitude of the position vector. So I want to give you an introduction into vectors and how the formulas of vectors, how they work. So now you know what r hat is. R hat is simply the unit vector. So now let's use this formula to get the electric field. We already know the magnitude of the electric field. We calculated that to be 36,000 newtons per coulomb. What we need to do is determine r hat. Now, the position vector is a vector that points from the source or the origin. In this case, the source charge or the point charge is at the origin. So the position vector, I'm going to redraw it, is the vector that starts from the origin and it goes to the point of interest. The point is 3, 4. So the position vector, let me give you a generalized formula for the position vector. Let's say this is A, this is B. The position vector is going to be AI plus BJ. That's what it is. The magnitude of the position vector is going to be the square root of A squared plus B squared. In other words, the magnitude of the position vector is the length of the hypotenuse of this triangle. So in this problem, the position vector is simply 3i plus 4j. The magnitude of the position vector is going to be the square root of 3 squared plus 4 squared, which is basically the length of the hypotenuse, or the distance between the point charge and the point of interest. So the magnitude of the position vector is simply 5. Now r hat, the unit vector, is r, the vector r, or the position. There's so many words here. All right, let me start over here. I don't want to confuse you. So r hat is the vector r divided by its magnitude. Just like we calculate any unit vector. It's the vector over its magnitude. Whenever you take the vector and divide it by the magnitude, you get the unit vector, you get the direction. You could see it this way. So this vector, the position vector, has 2 components, magnitude and direction. The absolute value of r is the magnitude of the position vector. So we're taking the vector and we're dividing it by its magnitude. So these will cancel, and what we're left with is the direction, which is the function of the unit vector. A unit vector has a length of 1, but its purpose is to give direction to the vector that you're trying to describe or trying to calculate. So I want you to understand the concept of the unit vector. So whenever you see r hat, I want you to understand its purpose. All it is, it's a unit vector that gives the direction to the original vector. But now let's continue in our calculation of r hat. So r hat is going to be the position vector divided by its magnitude, which will give us direction. So it's 3i plus 4j divided by 5. So what I'm going to do is I'm going to take 3 divided by 5 and write it in its decimal form. 3 over 5 is 0.6. So we get 0.6i. And then 4 divided by 5 is 0.8. So this is going to be 0.8 times j. So this is the position vector. Its magnitude is always going to be 1. If you were to calculate the magnitude of, let me say that again. I think I said this was the position vector. That is the unit vector. So I want to clarify. If you were to take the magnitude of any unit vector, it's always going to be 1. So if you were to take the square root of 0.6 squared plus 0.8 squared, it's going to be 1. So multiplying the magnitude of the electric field vector by 1 will not change its magnitude, but it will give direction to that vector. So now that we have the unit vector, r hat, I want to show you another way in which you can calculate it. Earlier in this video, we calculated that angle to be 53.13. So r hat is also cosine of the angle measured from the positive x-axis times the unit vector I plus sine of that angle times the unit vector j. So r hat is simply cosine 53.13 times I plus sine 53.13 times j. So if you plug in cosine 53.13, that will give you 0.6. And if you plug in sine 53.13, that'll give you 0.8. So now you have two ways in which you can calculate r hat. So here are the two formulas. I'm going to highlight it in green. If you know the angle of the vector from the positive x-axis, you can calculate r hat, the unit vector, using this formula. If you don't know the angle, but you know the position vector, the best way to find r hat is this way. Because once you know the position vector, you can easily calculate the magnitude of the position vector. And when you divide those two, that will give you r hat. So those are the two ways in which you can calculate the unit vector of the position vector. So just to recap, r hat is the unit vector of the position vector. So this is the position vector. This is a unit vector. So r hat is the position vector divided by the magnitude of the position vector. So now let's finish this problem. So we have the magnitude of the electric field, which is 36,000 newtons per coulomb, times r hat, which is 0.6 I plus 0.8 J. So now we got to distribute. 36,000 times 0.6 will give us 21,600. And 36,000 times 0.8 will give us 28,800. So notice that we have the electric field vector in terms of I and j. So that's how we could use this formula to get the electric field vector. Now, let's talk about how we can get this angle from r hat. So the angle theta, we can take the arc cosine of the x component of the unit vector. So if we were to take arc cosine of 0.6, it will give us 53.13. Likewise, if we were to take arc sine of the y component of the unit vector, this will be the same thing, 53.13. So you can easily find the angle if you know the unit vector. So now what I'm going to do now is I'm going to just summarize everything that we've learned. So if we have a charge, the charge Q, and we want to calculate the electric field at point P, remember the electric field vector is going to point away from the positive charge towards point P. This is going to be the x component of the electric field, and this is the y component. And here is the angle. If you need to determine the angle, you could take the arctangent of the y component over the x component. But since you don't know EY or EX, it's better to do it this way. So relative to the origin, which is going to be the plus charge again, the position vector is going to be in the same direction as the electric field vector. This is going to be Rx, this is going to be Ry. And let's say point P is at, AB. So remember, A is equivalent to Rx, B is the same as Ry. the angle is going to be the arctangent of ry over rx, or b over a. And the position vector, which starts from the origin and is directed to some point P, it's going to be AI plus BJ. The electric field vector is going to be the magnitude of the electric field, KQ over R squared, times R hat. And remember, R hat is simply a unit vector whose length is 1. The magnitude of R is going to be the square root of A squared plus B squared. And R hat, the unit vector, is going to be the position vector divided by the magnitude of that position vector. So it's AI plus BJ divided by the square root of A squared plus B squared. So that's how you can use this formula to calculate the electric field vector. So those are all the equations that you need to know.